welcome back to our machine design series. We are talking today about bearing life. So far we've talked about ways to calculate contact stress in a static way, but now we're talking about predicting the number of revolutions that a bearing is capable of enduring before fatigue failure. And so this is going to be a bit of a different task to tackle, and that's because tests on seemingly identical bearings under seemingly identical operating conditions have shown us that we can get large variations in actual bearing life out of that. But there are some correlations that we will use to try and estimate or predict the number of revolutions to failure. Okay, so if we were to take some of the data that has been collected by researchers up to this point and plot it on an XY axis on a log-log scale, where the x-axis is the log of life in number of revolutions, and the y-axis is the log of force, then we would see that the points on this plot, they have some scatter to them, but largely they're going to fall along the same line. Okay, and this line is given by the equation F times L to the 1 over A power is equal to a constant. So F and L we've already defined. For A, this variable depends solely on the shape of the roller. So A is equal to 3 for ball bearings, and A is equal to 10/3 for roller or cylindrical bearings. Now, to select a bearing, you're going to need to use this equation to compare the rated bearing load and life to your desired bearing load and life. And we will find that information in a bearing manufacturer catalog. I forgot to mention this, I think, in the first video, but bearing catalogs are an excellent source of information for all things related to bearings. For example, the SKF manual, not sponsored, but the SKF manual has a full section in the beginning of the catalog that really describes a lot about how bearings work. You could read it almost as a textbook on bearings. So I'm sure many manufacturers have that same feature in the front of their catalogs, and it is an excellent resource for information. But back to the lesson. So we need to select a bearing. Okay, so writing this same equation that we have above here in the plot, but now just relating two different pairs of force and life, one for the rated life and one for the desired life, we get an equation that looks like this, where L is in units of revolution, which if we wanted to convert it to life in hours, we could convert it using this equation, 60 times, do a cursive L times N, where this is the life in hours. And N represents the speed in RPM. 60 is just a conversion from minutes to hours. So we could combine these two equations and create one sort of master equation that we can use to relate the rated force, rated life, rated speed to the desired parameters. Okay, this is a really important equation. That's why I boxed it in this big blue box. And we are going to use this equation time and time again in the rest of this course to convert from a catalog rating into a desired load rating, or vice versa. So a couple notes about these variables. The catalog rating load, FR, is a radial load, so not an axial load. This is the radial load that causes 10% of a group of bearings to fail at the bearing manufacturer's rating life. Okay, so this is a reference value. It is not the actual load that is achieved by a particular bearing, and it comes with an inherent 90% reliability rate. So when you see these catalog ratings reported, keep that in mind. The catalog rating life is the life that those 90% of bearings can be expected to achieve at the rating load. So typically the rating life will be provided by a manufacturer, and it'll be standard across all of their bearings. So for example, SKF reports their rating life in 10 to the 6 revolutions. So they will report a load that you can expect 90% of a group of bearings to be able to withstand for 1 million cycles without any signs of fatigue. And again, that's at a 90% reliability rate. If we would like to have a reliability other than 90%, we can use a multiplier in the above equation here. So I'm going to just rewrite it once again with this multiplier A1 out in front. Now, this is sort of a shortcut way to do this. It's an estimate. Often you will see people do Weibull analyses. We're not going to get into that in this class, but if you are curious, there's a section in your textbook that describes how to do that. For us, though, we are going to use this table that comes out of an ISO standard that gives us some simple multipliers that we can put out in front of our standard bearing life equation to get reliabilities higher than 90%. Okay, so for a reliability of 90%, of course, A1 is equal to 1. This is the base form of our original equation. For 95%, it's 0.64, 96%, 0.55, 97%, 0.47, 98%, 0.37, and 99%, 0.25. So the drop-off is pretty drastic. If we want a reliability of 99%, then we're only going to get 25% out of this original portion of the equation. Okay, here's our example question. We are going to consider an SKF ball bearing, and we have an application where we desire a life of 5,000 hours at 1725 RPM with a load of 1792 newtons. And the question asks us, what catalog rating should we search for in the SKF catalog? And then we have a picture from that catalog with one particular bearing that we could consider, and we're asked, does this bearing meet the requirements for our application? So we can use the equation that we have looked at already. We are going to use the base form of the equation. We are just looking for reliability of 90%. I should state that in the problem statement, perhaps. Reliability of 90%. Okay, so let's write our equation. Now on the rated side, I'm going to use FR times LR to the 1 over A power. This was the first form of the equation that we saw. And then on the desired life side, I'm actually going to go ahead and use the conversion into life in hours and speed in RPM, because that is what we are given for our desired life and our desired speed. So we know our desired load is 1792 newtons. We know our desired life is 5,000 hours. We know our desired speed is 1725 RPM. And we need one more thing to be able to solve this, well, two more things actually, to be able to solve this problem. First, we need the rated life, which since we've selected SKF as the bearing manufacturer, we know that this is going to be 10 to the 6th revolutions. That is standard for all SKF bearings in the catalog. And the other thing that we need is A. So this is our exponent, and we have decided that we are going to select a ball bearing that's given in the problem statement, which, if you remember, that means that our A is equal to 3. If we had selected a roller bearing, then it would be 10/3. Okay, so we have enough to solve this equation for the rated load. Let's do it. Okay, so solving for FR here, we end up with 14,387 newtons, or 14.4 kilonewtons. So that is the rated load that we would need to search for in a catalog for this application. Now going up to this section of the catalog for this particular ball bearing that we are examining, we need to look at the basic load rating, and we're looking at the dynamic load rating here. So looking for this particular bearing, we have a dynamic load rating of 12.5 kilonewtons. If we go back to what we're solving for down here, we got 14.4 kilonewtons. So this particular ball bearing is not going to meet the requirements. We're going to need a higher load rating for this particular application. All right, so that's all I have for this video today. I hope it was helpful. In the next one, we'll start talking about combined loading, so what you can do to combine radial and axial loads to get a sort of equivalent load that you can then use in an analysis to predict bearing life. So I hope to see you in the next one.